Molecular orbital theory is going to be the most advanced bonding theory that we'll look at in this course. It's useful for describing things like excited states of molecules, the color property of molecules, that kind of thing. The idea is that when atoms interact or bond to form molecules, all of the individual atomic orbitals from all of those atoms have wave functions that can interact to form a set of molecular orbitals, and these orbitals are not localized to the atoms anymore, but cover the entire molecule. And we'll talk about them in regard to two atom systems, diatomic molecules, and we'll save the harder stuff for organic chemistry, although the concepts will be very similar. So the first idea is that orbitals of similar energy are going to interact most easily. The second thing to consider is that two atomic orbitals will interact to make two molecular orbitals. That is, the number of atomic orbitals from your atoms has to equal the number of molecular orbitals in your molecule. So if we draw this in terms of an energy level diagram, you'll get something like this. Each atom provides an atomic orbital, and the orbitals will interact to make molecular orbitals. So traditionally, the way this is done is you draw the atomic orbitals from the atoms on the outside, and you draw the molecular orbitals that result from their interaction in the middle. So the way it works is when you make molecular orbitals, one molecular orbital will be higher in energy than the atomic orbitals, and one will be lower in energy. And the reason this happens is because your atomic orbitals can be represented by wave functions. And when wave functions interact with one another, they behave just like any other wave, in the sense that you can have constructive overlap or interference and destructive overlap or interference. And the destructive interactions, the destructive overlap, produces a higher energy antibonding orbital, while the constructive interaction, the constructive overlap, results in a lower energy bonding orbital. And occasionally you'll see these types of diagrams drawn with dotted lines connecting the relevant molecular orbitals to their relevant atomic orbitals. We can draw something similar to this for the H2 molecule. So now I've drawn an atomic orbital for one of the hydrogen atoms. The other hydrogen atom that's involved in bonding to make the H2 molecule also has a 1s orbital, and it will be identical in energy because it's an identical atom. So now, when these hydrogen atomic orbitals interact with one another to make the molecule, you have two different types of overlap. You have constructive overlap, which will be lower in energy. So I'll draw the nuclei first. The constructive overlap is going to have most of the electron density between the nuclei. And what that looks like is pretty similar to what you would get if you just smushed two spherical things together. You get something that looks kind of tubular. So most of the electron density is going to be between the nuclei, which means the nuclei are going to be pulled towards one another. The antibonding molecular orbital that forms is going to look a little bit different. Again, the nuclei will be in the same place, but the electron density will now be on the outside of those nuclei. And what happens now is that the electron density is on the outside of the nuclei, so the nuclei are pulled towards the electron density, which means they're pulled away from one another. So this kind of overlap is destructive. It's pulling the atoms apart. And the bonding molecular orbital, the lower energy orbital, is pulling the nuclei together. It's creating the bond. Now, it's important to note that I've drawn these orbitals all separately in terms of an energy level diagram, but in reality they're physically on top of one another. They're not separated in space. You would have your two nuclei, and the bonding molecular orbital would surround them. And you would have your nuclei, and the anti-bonding molecular orbital would surround them as well. Now, you don't have to draw the spherical and tubular and almost spherical kind of shapes for all of these orbitals. You can also draw them with simple line diagrams. So this is the exact same molecular orbital diagram for the hydrogen molecule. We have the 1s atomic orbitals on the outside, and we have the molecular orbitals on the inside. So again, the lower one is bonding, and the upper one is anti-bonding. So whenever you see a star in a molecular orbital diagram, that indicates an anti-bonding orbital. And these are sigma-type molecular orbitals because of the type of overlap that's happening. The sigma-type label is representing overlap that is end-to-end or rotationally symmetric, where if you rotated these orbitals, it wouldn't break the overlap. So this is exactly the same type of label that you would use in the valence bond or hybrid orbital type theories, where sigma are those end-to-end overlaps and pi are the overlaps where if you rotate the bond, you break the overlap. Now, we can also use diagrams like this as electron configurations, just like the electron configurations that we've seen before. Each hydrogen atom has a single electron, or a 1s1 configuration. And what we can do then, to represent this in terms of our molecular orbital diagram, is to give each hydrogen's atomic orbital a single electron. Now, because the molecule has two hydrogen atoms, it's going to have two electrons, the number of electrons that came from the hydrogen atomic orbitals. So we fill the molecular orbitals exactly as we would do when we're doing other electron configurations. You fill from lowest energy to highest energy, you pair opposite spins, and those general rules. So now we have our two electrons in our molecular orbitals. So another way you could write this is to say that H2, the H2 molecule, has a sigma 2 configuration. And then after hydrogen, we encounter atoms that now have p orbitals in addition to s orbitals. And you can see the molecular orbitals that are going to result when p orbitals interact. So when p orbitals interact, you can have end-to-end overlap, or you can have side-to-side overlap. So you're going to get a couple of different types of molecular orbital. You'll get end-to-end overlap. So you'll have two p atomic orbitals interacting, and they'll overlap, and they'll interact to form a bonding orbital and an anti-bonding orbital. Again, the little dots are going to represent the nuclei. And again, note that the bonding orbital has most of the electron density between the nuclei, and the anti-bonding orbital has most of the electron density outside the nuclei, pulling them apart. And the labels that we give to these are going to be sigma. So the bonding is a sigma p molecular orbital, and the antibonding one is going to be a sigma star p orbital. And typically we include the n value as well. So normally we'll be working with carbon-based systems, so this would be a 2p orbital. So the sigma 2p and the sigma star 2p. And these are sigmas because they're rotationally symmetrical. The other two overlaps that can happen with p orbitals are the side-to-side overlaps. So you can have direct side-to-side overlap where they're aligned vertically, and you end up with a bonding and an antibonding orbital. In the bonding orbital, it's hard to draw in 2 dimensions, but you can imagine that some electron density is going to be above and between the nuclei and below and between the nuclei. So the net effect is that the nuclei are pulled towards each other. In the antibonding orbital, you have a somewhat more easy to understand situation. In this case, you have the nuclei, and the electron density is clearly on the outside, pulling the nuclei apart from one another. Because these are side-to-side overlap, they are pi labeled. So you have a pi 2p and a pi star 2p. The other type of p to p overlap that's side-to-side is when you have the p orbitals oriented coming into and out of the page. And the structures for these molecular orbitals are exactly like the structures we just drew, but rotated 90 degrees. Because p orbitals come in sets of 3, we have to draw the resulting molecular orbitals accounting for that. We'll typically draw 3 lines representing the individual p orbitals. So when you build the molecular orbitals from these atomic orbitals, you're going to have the side-to-side interactions giving you molecular orbitals with identical energy. And the end-to-end interaction is going to give you molecular orbitals with a slightly different energy. Not a very significant difference though.